In this lecture, we're going to cover gravitational potential energy, kinetic energy, and elastic potential energy, also called spring potential energy. Kinetic energy is the energy of an object in motion. The formula for kinetic energy can actually be derived by using a kinematic equation and the gravitational potential energy. But in this case, we just need to remember that the kinetic energy for objects in motion linearly is 1/2 mv squared. Also, another type of potential energy that we can talk about is derived based on Hooke's law. Hooke's law says that the force due to a compressed spring is equal to minus kx, where k is the spring constant and x is the displacement of the spring. The negative tells us that it's a restoring force. So from that, we can get the spring potential energy, which is 1/2 kx squared. Again, the k is the spring constant. That's a number in newtons per meter that depends on the type of material that the spring is made of. It tells you how stiff or how loose the spring is. X, again, is how far the spring is compressed or how far it is stretched. Both of these both of these energies, kinetic energy and spring potential energy, both are energies and therefore have the units of joules. We can now solve problems with gravitational potential energy, kinetic energy, and spring potential energy in 2 dimensions using what we've covered so far in this chapter. The key is understanding how these different forms of energy depend on their components along the x and y axes. First, we're going to look at gravitational potential energy. If an object is moving along an incline, does its potential energy depend on the displacement traveled along the incline? No. Remember, the gravitational potential energy only depends on the vertical displacement. The incline displacement is not important, only the vertical displacement. Now you may argue, well, wait a minute, I need to know the incline displacement in order to figure out the height of the incline, or how high the object moves. And that would be true. But the displacement itself is not needed. So what about kinetic energy? As with all energy, kinetic energy is a scalar quantity. But be careful. In the formula, it says 1/2 mv squared. V is the velocity, or at least the magnitude of the velocity. Velocity is a vector quantity. When we perform calculations of velocity from kinetic energy and gravitational potential energy, we need to be careful to relate the change in gravitational potential energy only to the change in kinetic energy in that same direction. Thus, it only affects the velocity in the y direction. Okay, so be very careful. Kinetic energy in the x direction has no relationship to the gravitational potential energy. Now, what about spring potential energy? Well, in the case of that, the amount that the spring is compressed or stretched is the important variable here. So no trigonometry is required. Kinetic energy will either use the vertical displacement of an object it covers, or the actual displacement of the object from the spring's force. So, when we talk about relating potential energy that's caused from the force of gravity with kinetic energy, we only want the vertical displacement. When we talk about spring energy, then we want to look at the total displacement of the actual displacement of the object. So let's work a couple of problems so you can see what we're talking about. A projectile is fired at an angle of 45 degrees. Which factors are important in calculating the maximum height the projectile reaches by using the conservation of energy? Go ahead and pause the video now and see if you can come up with the right answer. The correct answer is C. Only the y component of the velocity is important when using gravitational potential energy and conservation of energy when finding the height. A spring launcher fires a marble at an angle of 52 degrees. In calculating the energy available for transformation into gravitational potential energy and kinetic energy, What value of x is used in the spring potential energy equation 1/2 kx squared? Pause the video now and choose your answer. Let's see if you chose the correct answer. The answer should be C. The straight line displacement of the spring. Remember, this is independent of x and y when talking about kinetic energy. What is the final velocity of a box of mass 5.0 kilograms that slides 6.0 meters down a frictionless incline at an angle of 42 degrees with the horizontal? The system will be the block. Since there's no friction, there are no external forces acting on the block, and we can use the conservation of energy. The gravitational force will take care of the gravitational potential energy. What types of other energy are involved here? Only 3 types of energy have been discussed so far, and in this case, there isn't any spring. So that means only gravitational potential energy and kinetic energy. So we're going to go ahead and look at what we start with and what we end with. We start with a velocity of 0 meters per second. We end up with a velocity, well, we don't know. We know that the displacement of the incline, or from the top to the bottom, is 6.0 meters, and we know the angle of the incline is 42 degrees. We take the initial energy we start with, set it equal to the final energy that we end with. Notice here that these terms here are going to cancel out. So this spring potential energy and this spring potential energy are 0, and we're left with kinetic energy and gravitational potential energy we start with has to equal the kinetic energy and gravitational potential energy we end with. To save on subscripts, we'll assume that no subscript implies a final quantity. So in other words, KE will equal KE final. At the top, do we have any kinetic energy? No. At the bottom, do we have any potential energy? No. So that means if we put in the equations that we have 1/2 mv naught squared plus mgh naught equals 1/2 mv final squared plus mgh final. We know that the initial velocity is 0. Be careful, that's right, we have to solve for the height of the incline, which is actually going to be d sine theta. That gives us a height of 4.0 meters. Our final height is 0 meters. So now let's go ahead and solve for the final velocity. Notice here that my initial kinetic energy is 0, my final potential energy is 0, and that gives us v squared equals 2gh. If I take the square root of both sides, I end up with 8.9 meters per second. The velocity at the bottom of the incline is 8.9 meters per second. The direction is going to be down and at an angle. Okay? So when we say the velocity is 8.9 meters per second, we have to keep in mind that there is the direction, and that's the direction into the ground. Consider the incline plane problem that was just worked, but now add a spring at the bottom of the incline. The spring will be compressed a distance delta x and then released. Find the velocity of the block when it rises back to where it was first compressed at a height of delta h. What energies do we need to consider for this problem? Once compressed, the box has spring potential energy, gravitational potential energy, and 0 kinetic energy. When it loses touch with the spring at delta h above its fully compressed point, it will have kinetic energy, gravitational potential energy, but the spring's potential energy will be 0. So again, we start with the energy we start with, kinetic energy, plus spring potential energy, plus gravitational potential energy. This is what we start with. What we end with is kinetic potential energy. I'm sorry, that should be kinetic energy, not kinetic potential energy. There's no such thing. So kinetic energy plus electric potential energy plus gravitational potential energy. And this becomes a spring potential energy plus gravitational potential energy to start with. And then we end with kinetic and gravitational potential energy. Before we proceed further with the solution, Let's think how hard this problem would be to solve without using conservation of energy. Once the object is released and the spring starts moving away from its compressed state, the force is no longer constant. It will require mathematical integration or calculus to solve. Free-body diagrams are not the best way to find the velocity of the object. They're great in finding forces or the net force, but not velocities. Let's put in the equations and rearrange them to solve for the velocity. We have spring potential energy plus gravitational potential energy, and that's equal to kinetic energy plus gravitational potential energy. Solving for the velocity, we end up with the square root of k over m x squared minus 2g delta h. Here, remember, delta x and delta h are two different things. We now have the equation for the velocity when the block rises a vertical displacement of delta h. But if we're only given delta x, how do we find delta h? That's right, trig. A box on an incline is in contact with a spring. The box is released, compressing the spring. For every increment delta x, the box moves down the incline. How much does its height, delta h, change? Okay, go ahead and pause the video and see if you can come up with the right answer. Okay, let's check and see if you were right. The answer is C, delta x sine theta. Great job if you got it right. A box is held on top of a spring on an inclined plane of angle 31 degrees. The box is released, compressing the spring. If the spring moves 7.0 meters down the plane, how much does its height, delta h, change? Pause the video now and solve for the answer. Let's see if you were right. The answer is D, 3.6 meters. A box of mass m is on an inclined plane that makes an angle of theta with the horizontal, and it's in contact with a spring constant k. The box is released and it compresses the spring an amount of delta x before rebounding. In terms of m, g, k, and theta, what is the value of delta x? Go ahead and pause the video now and solve the problem. Okay, let's see if you were correct. We start out with gravitational potential energy. We end with spring potential energy and gravitational potential energy. We then have mgh naught is equal to 1/2 k delta x squared plus mgh. We go ahead and solve for delta x by using algebra, and we end up with 2 over k mg sine theta. A spring with a spring constant of 150 newtons per meter on an incline of angle 54 degrees is compressed a distance of delta x, which equals 0.060 meters, along the incline by a mass of 0.042 kilograms, and then released. What is its velocity when it passes the point where it was first compressed and loses touch with the spring? Go ahead and pause the video now and solve the problem. Okay, let's see if you have the correct answer. We start out with spring potential energy plus the plus the gravitational potential energy. That's equal to the kinetic energy plus the final gravitational potential energy. Solving for V, we end up substituting in our numbers with 3.5 meters per second. If you ended up with the correct equation but not the correct answer, make sure that you did the following. Make sure that you squared the delta x. Make sure that you took the square root of the answer. Make sure that you use parentheses for this. You don't need parentheses here or here, but you do need to have a parenthesis around this and around this if you're subtracting them all in the same line. A marble launcher shoots a marble vertically and then shoots a marble in the horizontal direction. Describe why the exit velocity of the marble in the two cases is different. Which exit velocity is greater? Pause the video now and solve the problem. Okay, let's check and see if you have the right answer. In both cases, the spring potential energy is the same. For the vertical case, though, part of the potential energy from the spring is transformed into an increase in gravitational potential energy, as the exit point of the marble is higher than its compressed point. In the horizontal direction, there is no change in gravitational potential energy. So the spring potential energy is transformed totally into kinetic energy. The marble's velocity is greater in the x direction. In the next video, we'll talk about conservation of energy and problem solving.